Hey guys, welcome back. So till now we have learned two conditions of AVL tree, that is left left and left right. Hope both of the conditions are clear. Now in this video let's learn the third condition, that is right right condition. Now as the name indicates, it is exactly opposite or a mirror image of a left left condition. So let's see how. So let's say this is the AVL tree. So right now this AVL tree is a balanced one, so we are good, no problem. Now let's say we are inserting number 70 in this tree. So after inserting, this is how it will look like. So 70 becomes the right child of 60. Now as we already said, every time we do an insert, we have to see that is there any node which is disbalanced because of insertion of this new node. So let's see. 70 is a leaf node, no problem. 60 left is -1, right height is 0. -1 and 0 difference is 1, we are good. This node's left height is -1, right height is 1, difference is 2. So we have a problem. So we can say that this node over here is disbalanced. So if it is disbalanced, we have to balance it. How do we do that? Using a rotation. Now which rotation I have to do? For that we have to see which condition this problem falls into. For that the simple question is, which grandchild of this node has the max height? That is the node which is creating a problem. So in this case the only grandchild is this guy over here. So this is the culprit. And how do we reach this culprit over here? Right and then a right. Hence we can say that this is a right right condition. Now what do we do in case of a right right condition? We do a left rotation. So we do a left rotation on this node. So 50 will come down, 60 will go up, and 70 will also go up. So after doing a right right rotation, this is how the tree will look like. 50 came down, 60 went up, 70 came up. Now after doing this, we see that all the nodes are balanced. These two over here are leaf nodes, no problem. Height of this is, here it is 0, 0, so we are good. Left height of this is 0, left height of this is 1, difference is 1, we are good. So this is how we do a right right rotation. Now we quickly went through this because this is a mirror image of a left left condition. So there is nothing much to explain over here. Now if we quickly see the notes over here, it says the same thing. That is, in case of a right right condition, we do a left rotation. And how do we find if it is right right condition? Right right node from current disbalanced node is causing a disbalance. Then we say that this is a right right node. Or in other words, whichever grandchild of the disbalanced node is having the max height can also be used to determine the condition. So I hope you have understood the right right condition. Now let's see one more example of a right right condition. Now let's say this is our AVL tree. So right now this is balanced, so we are good, no problem. Now let's say if we want to insert number 80 in this tree. So after inserting 80, this is how it will look like. Now after inserting 80, we see that there is a disbalance problem in this tree. And where is the disbalance? The disbalance is happening at this node. Left height is 0, right height is 2, difference is 2. So we have a problem. So to solve this problem, now we have to do a rotation. Now how do we identify which rotation we have to do? That we will get to know from which condition this problem is falling in. Now what is the condition this problem is falling in? It is right right. And how did we determine that it is right right? See, the grandchild of the disbalanced node whichever grandchild of disbalanced node is having max height. So here luckily we have two grandchild. Height of this one is 0, height of this is 1. Now since the height of this grandchild is 1, we can say this grandchild is the culprit. And how do we get to reach this grandchild? Right and right. So this is a right condition. Now what we do in right condition? We already learned we have to do a left rotation. After doing a left rotation, this is how the AVL tree will look like. So 60 from here gets promoted, 70, 80, 50 everything gets promoted, and 40 and 30 gets downgraded. That's what we are seeing here. 60 is the new root and rest of them are as shown in the diagram. So I hope you have understood the right condition. Now let's see the algorithm for this condition. Now as you would have already guessed, this left rotate algorithm is exactly same as what we have seen in the previous video, that is left right condition. The only difference over here is the parameter that we are passing. In the previous left rotate we saw that the parameter that we were passing was the disbalanced node's left child, but in this case we are passing the disbalanced node itself. Rest of them remains as it is. So what is the current disbalanced node? It is 40. New root is equal to disbalanced node dot right. Disbalanced dot right is 60. So this is the new root. Disbalanced node dot right is equal to disbalanced node dot right dot left. Disbalanced node dot right dot left is 50. This gets assigned to disbalanced dot right. That is, this starts pointing over here and this reference gets cancelled out. New root dot left is equal to disbalanced node. New root is this 60. Dot left, this starts pointing to 40. So this reference gets cancelled out. So 60's is the new root, left child is 40, 40's left is 30, right is 50. Now that's the exact same thing we see over here. 60 is the new root, left child is 40, left is 30, right is 50, and this remains as it is. Fine. Now let's quickly see what is the time and space complexity of this algorithm. Now again, all that we are doing in this algorithm is changing some reference variables here and there. So time complexity for that is order 1. Space complexity again is order of 1 because we are not using any extra space for this operation. So with that we have understood the right condition as well. Now in the next video let's see what is right left condition and how do we handle it. Thanks for your time. See you in the next video.